right, we've already discussed differential rate laws, which take the form that you see in this column over here. But now we want to talk about integrated rate law, which is a different form of the same information that relates the concentration of a single reactant and time, unlike my differential rate laws, which you remember related concentration and rate. If you know the integrated rate law, you can go back to the rate law. And if you know the rate law, you can go forward to the integrated rate law. So, for example, if you know that this expresses your experimental data, that means you know that it's first order, the reaction is first order with respect to A, and you can write a first order differential rate law using that information. Similarly, if I know that my reaction is second order with respect to A, I can write out an integrated rate law using this relationship. You will pretty much just have to memorize these unless you know a little bit of calculus. They have a form on the equation sheet, but I would keep in mind, I think that this form is a little bit more useful, and it's just 3 equations. I'd be tempted to memorize this. Okay, why would you ever use an integrated rate law? We just spent some time getting really comfortable with the differential rate laws, or maybe starting to get comfortable with the differential rate laws and the dependence of rate on concentration. Why are we suddenly looking at time and concentration? Well, remember that all rate laws are experimentally determined. So whether we get an integrated rate law or a rate law from experimental data is pretty much just going to depend on whether it's easier to collect time data, time-dependent data, or to collect rate data. We can talk more about what those experiments might look like in class. For right now, let's just start exploring some of the pieces of an integrated rate law. Let's start with a first order rate law. So you can see that the first order rate law looks like this. That little 0 means initial concentration of A. Okay, obviously K, that's our rate constant. Little t is time. Ln is natural log. If you look at this is in the form of y equals mx plus b. If you look at all the integrated rate laws take that form. And what that means is that the slope of all of these rate laws is related to the K, related to the rate constant for the reaction. I just said slope, so I'm getting a little bit ahead of myself here. This also kind of leads us to what kind of data I would be dealing with if I was looking at an integrated rate law problem and how I would deal with it. Anytime you have integrated rate law data, essentially you're going to have, concentration and time data like this. 0, 30 seconds, 60 seconds, etc. You'll have concentration starting at like 1.0 molar, 0.9, 0.8, whatever. Okay, and if you plot that data in 3 different ways, so you'd have to plot it like this, concentration versus time. You'd have to plot it like this, the natural log of the concentration versus time. And finally, 1 over concentration versus time, right? Essentially what we're doing is we know that each of the integrated rate laws takes each of these forms. Whichever of these graphs of the data is linear, is going to be what rate law it is. So for example, if I'm looking at this plot and I see this, and then I see this, and then I see this, something like that, I know that I have a 0 order reaction. with respect to A. Sorry, respect to A. Okay, so anytime you have integrated rate law data, so time and concentration data, you want to plot it, and then you want to look for the line. And whichever the y-axis is what's going to tell you which order it is. Okay. Let's talk about half-lives. This is an interesting topic. We can use the integrated rate laws to look at half-life. Now, half-life is defined as the time required for a reactant to reach half of its original concentration. That can be expressed mathematically, in my generic equation, right? If I have a concentration of A, concentration of A at the half-life is going to be equal to 1/2 of the initial concentration of A. Okay? This means that we can actually derive from the integrated rate law equation. So, for example, the 0th order integrated rate law equation is concentration of A is negative KT plus A 0. Okay, I can actually substitute in for my concentration, the initial concentration over 2 at the half-life, and then solve. I'm going to put little 1/2 next to the T now because this is the half-life time. I can actually solve for time and figure out what the half-life is for a 0th order reaction. So let's just do that really quick. So minus A sub 0, so we're going to have negative 0 over 2, I think, equals negative KT 1/2. I hope I haven't taken too many shortcuts. Positive, positive. Yeah, this looks right to me. 2K equals T 1/2. Okay, let me check my math really quick. Haha, I was right. All right, so you can actually derive that. The thing to note here is that the half-life of a 0-order reaction is dependent on the initial concentration of the reactant. This is not the same for first order. So first order ends up solving out, and you can prove it to yourself if you want by using this relationship up here, and the natural log of A equals negative KT plus the natural log of A0. Okay, so you can do the same derivation I just did for 0th order if you want. But I'll tell you that the answer ends up being 0.693 over K equals T 1/2. You'll note that then a first order half-life is not dependent on the starting concentration. This is the kind of half-life that most of you are used to talking about and used to seeing. It's a constant half-life. That time will always be the same no matter what you start with. This is the type of half-life we're talking about when we're talking about nuclear decay. That's a first order decay. All right. Last but not least, our second order half-life, I'm pretty sure this information is on your equation sheet, but I'm just going to throw it out there, is 1 over K A initial. In class, we'll talk about the conceptual meaning behind these half-lives and why it makes sense with respect to the kinetics of the reaction. Last but not least, you can use this trick anytime they ask you a question like determine concentration determine the time at which the reaction is, for example, 40% complete. We use the same trick as we use for deriving a half-life. All we have to do is say, well, if it's 40% complete, that means the concentration of A at that point is actually 0.6%, well, is 60% of A, right? If it's 40% complete, it's 60% of the initial concentration left. And then we can do the substitution and figure out what the time is at that point. Okay, so there's a lot of power in being able to make that kind of substitution. Last but not least, in case you haven't noticed, we've kind of been looking at a bunch of reactions that seem to have the reactant A and maybe no other reactants going to B. But it's also possible to look at a change in concentration, or rather, it's possible to use an integrated rate law to get data about something that looks more like this. Sorry, C plus D. You just have to be kind of careful and you have to be clever about it. So if you have two reactants, and it's still most convenient to collect data in the form of time and concentration, then what you're going to want to do is you're going to want to make one reactant in large excess. Okay, what do I mean by that? I mean that maybe we make A, the concentration of A that we start with 2.0 molar. Maybe we make the concentration of B that we start with 0.001 molar. Why does that help us? Well, it means that if we're looking at the change in concentrations over time, and let's say we have a break in the graph right here. So like, let's say this is where 0.001 is the initial concentration of B, and let's say kind of up here is where 2.0 molar is. Over the time scale of this reaction, B is going to noticeably decrease. A large percentage of it is going to decrease over time. Whereas 2.00 whatever molar, it's pretty much going to stay exactly the same. Yes, it'll decrease in concentration a little bit, but not nearly as much as B will end up decreasing in concentration. What that means is when you're looking at the real rate law, the differential rate law, rate equals K times concentration of A times concentration of B, we can end up looking just at the order of B. See, that's N up there. We can look up just at the order of B because the concentration of A is actually constant over the time scale of the experiment. So what does that mean? That means this whole piece here we could think of as some other constant. And we could express that the rate is equal to that constant times B to the M. All right, we can use the integrated rate laws. We can plot this data, figure out which graph is linear. So let's say it ends up being first order. Again, we can't tell just from looking at that. I just made up that data. Let's say this data ends up being first order, in which case our integrated rate law would be natural log of B is equal to negative K prime, right, because we're actually solving for this constant, which includes that constant concentration of A, K prime T plus natural log of the initial concentration of B. Our major lab in this unit is going to involve what's called a pseudo rate constant. That's what that K prime is. And for example, in this expression, we would say that this equation was pseudo first order because we actually don't know the order of A. It could have an order too, but written like this is a pseudo first order reaction. We'll discuss more in class.